Exercises 4.5 and 4.6, we're taking a look at matrices and transformations using matrices. To be honest with you guys, matrix addition and subtraction by hand isn't required as part of the study design, but I think it's important to have a really good understanding of how it all works so that you're able to apply matrices for what is required in describing transformations. All right, let's first of all consider what a matrix is. So here we have an example of a matrix. You can see it's got some square brackets and some numbers in there. Now this is an example of a 2 by 1 matrix. It's 2 rows by 1 column. Here we have matrix A, and this is an example of a 2 by 2 matrix, 2 rows by 2 columns. In order for us to do matrix addition, the matrices need to be of the same size. Otherwise, it's not possible. If I've got A plus B, I write down matrix A, I write down matrix B, and then it's simply a matter of adding the corresponding elements. So 1 and 5 gives us 6, 2 and 6 gives us 8, 3 and 7, 10, 4 and 8, 12. So very simple. Matrix multiplication is a little different. I'm going to start by thinking about the number system. 3 times 2 is exactly the same as 2 times 3. The order is not important. But with matrices, it's very important. So what we come up with is that matrix A times matrix B is not the same thing as matrix B times matrix A. Here, for matrix A, it's an example of a 2 by 3. For matrix B, this is an example of a 3 by 2. Now, I want you to write on top of these matrices, please, for A times B. We've got obviously matrix A, and we've got matrix B there. But in your notes, can you please write that this is a 2 by 3? So I want you to write 2 times 3 and put that in brackets. Being multiplied by, so multiplication symbol. Open up brackets, 3 by 2. All right, if matrix multiplication is possible, the 2 inners will be the same. So you should have 2 3s, they're the 2 inners. The result of your matrix is going to be what the 2 outers are, so a 2 by 2. So you can see that the result of my matrix is going to be a 2 by 2 matrix. And it's going to be possible to perform this matrix multiplication because the 2 inners are the same. All right, how did I get this 11? Well, what it was the first row multiplied by the first column. So 2 times 4 plus 3 times 1 plus 4 times 0. And that goes in here. How did I get the 18? Well, it was the first row by the second column. So 2 times 0 plus 3 times 2 plus 4 times 3. How did I get the 26? Well, it was the second row by the first column, so 5 times 4 plus 6 times 1 plus 7 times 0. And the 33, well, that was going to be the second row multiplied by the second column, so 5 times 0 plus 6 times 2 plus 7 times 3. And that's how we do matrix multiplication. You can do this using your CAS calculator. To be honest with you, I wouldn't be defining these matrices. I find that a complete waste of time. Instead, I'd just suggest you put them in once, the matrices, and if need be, just use copy and paste to do further calculations. Now, let's start looking at the transformations. We're saying here that matrices can be used to describe transformations. The transformations that we'll consider will be dilations, reflections, and translations. So we should have a really good understanding of what all of those kind of transformations are. We'll be performing these translations on coordinate pairs, x and y values, where x is an element of R and y is also an element of R. We will say that the point xy is mapped onto the point x prime, y prime. So this here is the transform point. So this is the original point, and then through the transformations it becomes another point, and we denote it as being x prime, y prime. Sometimes we might use x with a capital T, y with a capital T, just showing you that that's the transform point. We say the transformation is xy going on to x prime, y prime. Let's look at dilations. So x prime, y prime, the new x and the new y, will equal this matrix multiplied by the original point xy. If we perform matrix multiplication on it, you will see that we end up with x, k, y. So what we're looking at here is that this is a dilation factor of k from the x-axis, or if you like, parallel with the y-axis. Every y value has been multiplied by k. Dilation factor of m from the y-axis, so that is every x value is multiplied by m. So we've got x prime, y prime. This is the matrix that we'll need to multiply it by. There's an m there and a 1 there, zeros along here. This is the original point xy. If we do matrix multiplication, that will produce mxy. Dilation factor of k from the x-axis and m from the y-axis, so that's a combination here. So we've got zeros along this side. I've got an m there and a k here. If I do matrix multiplication, I end up with mxky. So the new x is going to equal mx, so m multiplied by the original x. The new y is going to be equal to k multiplied by the original y, where m and k are the dilation factors. Reflection. So if we're reflected in the x-axis, my new xy value is going to be the original xy being pre-multiplied by this matrix. A 1 here, zeros along there, but a -1 here. And look what happens when I perform this matrix multiplication. I end up with this matrix. So the new x value is going to just equal the original x value, but the new y value is going to equal the original y value being multiplied by -1. So that's a reflection in the x-axis. Similar idea for reflection in the y-axis, except for I've got a -1 here and a 1 there, and not surprising, look what it produces. And if it's reflected in the line y equaling x, we just simply want to interchange the x and y values. So we've got the new x and y values are going to equal the original, being pre-multiplied by this matrix. Zeros along the diagonal this time, and 1's there. And look what happens. The new x value is going to equal the original y value, and the new y value is going to equal the original x value. Translations are probably the easiest to understand. X prime, y prime, so the new x value. The new y value is going to equal the original x and y being added to this matrix here, A, B. So we have the new x is going to equal x plus A, and the new y is going to equal y plus B. Just some terminology, guys, too, that if we're looking at the transformation of the original point xy becoming the x prime, y prime, then r squared is used to represent the set of all real ordered pairs. So because it's got an x and a y, we're just using to the power of 2 there. It's only a bit of terminology. It does come up from time to time in some questions. So don't be confused when you see it written like this, f such that r squared becomes r squared. That just means that we're talking about coordinate pairs rather than just particular values. This, as far as all your transformations of matrices is concerned, this yellow table here is going to be your go-to for everything. All right, this is what you're going to be using all the time. Let's now take a look at our first problem, and we'll start applying these concepts. Problem 1. The point 2, -3 is translated by the matrix -4, 2. Find the coordinates of the new point. So, we're looking at a translation. We go to our yellow box here. Which one is the translations? It's here. X prime, y prime is going to equal the original xy plus the translation matrix. So that's what I set up. I know what that translation matrix is. It's -4, 2. So I write it down. And I now sub in what the original x and y values are. So x was 2, y was -3. So my new x value is -2 and my new y value is -1. So the point 2, -3 has been transformed to the point -2, -1, given that that was our original point and that there is the translation matrix that's been applied. Problem 2. Just ignore what I've got in green here, I'll explain that at the end. The point -5, 1 is translated first of all by this matrix and then reflected in the line y equaling x. Find the new coordinates of the point. So we have to do this in 2 stages. Firstly, we're just going to deal with -5, 1 being translated by this matrix and see what that produces. So again, I'm using the translation matrix, here it is, or the translation setup. So x prime, y prime is equal to the original xy plus the translation matrix, and so I achieve that here. And so I now know that the point -5, 1 will be transformed to -8, 6 if this translation matrix is applied. That's what we've shown. The next step is to take that as the input and then reflect it in the line y equaling x. All right, so I'm going to think of this now as being the original xy for my second stage. So the reflection in the line y equaling x. Again, I'm looking at reflection in the line y equaling x, and here's the matrix setup. The new xy will be equal to this matrix being multiplied by the original xy. So I set this up, but this time I think of the original x value as being -8. That's just the result of the first stage of my transformation. And the original y value as being 6. I do that, and I can see that the point -8, 6, the result of the first stage of the transformations, is now going to become 6, -8. So overall, what's happened? -5, 1 has moved to the point 6, -8. And that's the objective. Let's take a look at what I've written here in green. So xy is what we started with. We apply the translation to it. So we take away 3 from x and we add 5 to y. We now reflect it in the line y equaling x, so we just interchange the elements. We now sub the original in, so originally y was equal to 1, so 1 plus 5 gives me 6. And originally x was equal to -5, so -5 take away 3 gives me -8. So that achieves the same situation, but without the need of matrices. It's good to have a handle on both ideas. Problem 3, use matrices to find the image of the curve y equaling x squared under the dilation by a factor of 3 horizontally and 2 vertically. All right, so every x value has been multiplied by 3, every y value has been multiplied by 2. And when we're talking about the image, well, we've been given a rule here, y equaling x squared, so we want to find a new rule that takes into account these transformations. So the first job is to set up the matrices for the transformations. Notice that I've got a dilation factor for both horizontally and vertically. So if I go to my yellow box, I'm looking for dilation factors in both, and that's it here. So x prime, y prime will equal m and k, 0, 0 there, that matrix being multiplied by the original. So we're not talking about points, we're talking about rules in this case. So it's a little bit different, but just hang in there. So x prime, y prime will equal this matrix, the dilation factor matrix, being multiplied by the original matrix. So if I do that multiplication, I can do that on my CAS easily to evaluate, don't need to do it by hand. I'll get this. So x prime will equal 3 lots of the original x, y prime will equal 2 lots of the original y. So what I do next is equate and solve for x and y. So just need to follow that step. So we'll equate it. So x prime is equal to 3x. Now solving for x, I'm going to get x, the original, is going to equal the new one divided by 3. Y prime equals 2y. So solving for y, I get y prime on 2. Now I'm going to sub x prime and y prime into the original equation and solve for y prime. So I start with y equaling x squared, that's the original rule. But instead of y, I'm going to write what y is equal to. Y is equal to y prime on 2, so I write that down there. X is equal to x prime on 3, so I write x prime on 3. Now y prime on 2, just manipulating this here, if I square x prime, I'm going to get x prime squared, and if I square 3, I'm going to get 9. In my next move, let's multiply everything by 2. So now I have y prime, the new y prime, is going to equal 2 lots of the new x to the power of 2 divided by 9. Now remember, I'm after a rule, so I don't need to put the primes in here. I've got y equaling 2/9 of x squared. So the original image created by y equaling x squared will now be created by y equaling 2/9 of x squared. So this here takes into account the dilation factors listed in the question above. Note that instead of using matrices, you could use this alternate approach to work out what x prime is equal to and y prime is equal to. But you then need to take that information and do the rest of the steps that are given below here in blue. Use matrices to find the curve to which y equals 1 over x minus 3 plus 2 is mapped by a reflection across the y-axis. Okay, so we're reflecting the y-axis. So this is a hyperbola, but we're reflecting the y-axis. So we look at our reflection matrices, reflection of the y-axis. We're going to be using this setup, and that's our starting point. So x prime y prime is equal to this particular matrix from the yellow box being multiplied by the original. Performing the multiplication, you get this. And remember, the first job is to equate the new, so x prime is equal to negative x, and then solve for x. So let's divide both sides by negative 1s to get x is equal to negative x prime. Y prime is simply equal to y, so I've got y prime equaling y. There's no need to make any further changes there. Next stage, I'm going to sub the x prime, y prime into the original function. So I've got y equals, this is the original. But instead of putting in y, I'm going to put what y is equal to. So y is equal to y prime. And instead of putting in x, I'm going to put what x is equal to. X is equal to negative x prime. So that's it there. Now, I don't write that in terms of y prime and x prime. I just put in y and x now. Okay, and then just some manipulation there. I can write it as y equaling 2 minus 1 over x plus 3. So what we've really seen there is that the original y equaling this is going to become that, y equaling that, given the transformations described in the question above. In green, once again, as an alternate to using matrices, you can do it this way. But again, from this point forward, just do these steps in blue. Problem 5, there's a fair bit in this, and to get your head around it, you're really going well. What is the transformation for a translation of 2 to the right and 4 down? Then we have a reflection in the x-axis and a vertical dilation by a factor of 3 in that order. So notice it's in that order, so we can't just do it in dilations, reflections, translations. The question is very specific about the order that's required. So the first thing I'm going to deal with is taking the original xy and then applying this translation. So if I look at my translation down here, my x prime, y prime, that result will be getting the original and then adding the translation matrix to it. So I'm starting here. There's my original xy, and then I'm adding to it the translation matrix. So 2 to the right, so positive 2 for x, and 4 down, so negative 4. Okay? So the result of this inside this bracket will be the x prime, y prime, the result after the first step of the transformations, that is applying the translation, what I'm highlighting here in yellow. We'll get that. All right, now the next part is that we want a reflection in the x-axis. So if I go to reflection in the x-axis, here it is, my setup should be is that my new xy will be the original being pre-multiplied by that matrix. In my case, the original is going to be the result of that first stage. So the result of the first stage is here, and I pre-multiply that by this matrix. All right, and that will give me my new xy. So that will be the result after applying the first stage and now this second stage. That will be going here. Finally, the last stage of the transformations is to do with dilations. And so what I have here is a vertical dilation by a factor of 3. So that means every y value has been multiplied by 3. So if I look at dilation factors from the x-axis that is parallel with the y-axis, then here's my setup. I get my original, which in my case is going to be the result of the first two stages, and I pre-multiply it by this matrix, where k is the dilation factor. And remember that my result from here is going to be my original xy, which is in fact just the result of the first two stages, and I'm pre-multiplying it by this matrix, which takes into account that transformation there. So obviously what I could do is just put all of that into my CAS to spit out that answer, but just looking at what's going on from step by step, this here becomes x plus 2 and x minus 4. Then performing this multiplication, I get this. And now this multiplication by hand gives me this one here. So what have I got? My new x will be equal to the original x plus 2. My new y value will be negative 3 lots of the original y value taking away 4 from it. In B, apply the transformation to find what the curve with the equation y equals 1 on x squared is mapped under the transformation. So I'm going to use this information from part A, and that will feed into B here. So for B, x prime is equal to x plus 2. Solving for x, I get x is equal to x prime take 2. Y prime is equal to this, and solving for y, I get y prime over negative 3 plus 4. The original rule was y equaling 1 on x squared. Now, I don't want to write what in terms of y and x. I want to write it in terms of x prime and y prime. Y is equal to y prime minus 3 plus 4, so I write all of that down instead. And x is equal to x prime minus 2, so I write that down. First move, remember I want to get y prime by itself. I take 4 from both sides. I multiply everything by negative 3. And I write it in a different way, so I've got the positive part first. And now, finally, I write down the new rule in terms of y and x. So y is equal to 12 minus 3 over x minus 2 squared. So the original y equaling 1 on x squared, given all the transformations originally stated in the question, will become this instead. All right, in part C here, we need to map the point 3, 1 ninth through the transformations described. So this point here, 3, 1 ninth, is a point that is originally on this graph. Given all the transformations, where is that point going to move to? Please note the change there. It should be a 3, not a 1. So this point is going to become what? Well, we know the new x value is simply going to equal the old x value plus 2. So if I sub in 3 for x, I'll get 3 plus 2, which is 5. So the new x value is going to become 5. So that 3 is going to move to a 5. Y prime is equal to this rule here. If I sub in 1 ninth, then you can see through the manipulation here of numbers, then I get 35 on 3. So the 1/9 is going to move to a 35 on 3. So the 0.3, 1/9 is going to become the 0.5, 35 on 3. Now notice that in our earlier work, the y equaling 1 on x squared becomes this rule here under all the transformations described in the question. So in theory, if I substitute 5 into this original graph, if I substitute x equaling 5 into this transformed equation, then I should get 35 on 3. So it's a good little double check to make sure they haven't made any kind of mistake. If I do that, subbing in x equaling 5, then fortunately it produces a 35 on 3, which confirms that what I've done is correct. 6. Consider the function f where the domain is between -3 and 2, including -3, including 2, that maps out the set of all real numbers where f of x is equal to 4 minus x squared plus 2. When we look at the rule, we can see straight away that we got an upright parabola and that the turning point occurs at x equaling 4, y equaling 2. Our first job is to find the range of f, so to find what the y values are. There's the domain, what's the range? So here for A, that would be the graph completely drawn if there were no domain restriction. But the domain restriction given is that x is between -3 and +2. So you can see what the answers are obviously, but how do we calculate those? It's pretty simple. F of x is equal to 4 minus x squared plus 2, and x is between -3 and 2, including -3 and including the 2. So let's evaluate what f of -3 is. We get 51. F of 2 is 6. So I know that this position here is -3, 51, and this position is 2, 6. So our range is from 6 up to 51, and we are including both points, or both endpoints. So therefore, our range will be from 6 to 51 with square brackets. Okay, the graph of f, so this original f function here, is translated 2 units down, translated 2 units to the right, and dilated by a factor of 1/2 from the y-axis to become a new function h. We need to find the rule for h, so they are the translations. So for b, the new x, the new y, x prime, y prime. We'll start off with this here and take care of the translations. And we can deal with both of the translations at the same time. Here's our yellow box, and we're looking at the translations down at the bottom. So the new x, the new y is the original x, the original y, plus the translations taken care of. So in my matrix equation, I've got x and y plus 2 minus 2. So this represents a translation of 2 units to the right along the x-axis and 2 units down, obviously along the y-axis. That takes care of the translations. I would get that result, and that will be my new x and new y. The next stage of transformations is this dilation factor of 1/2 from the y-axis. So that is that every x value is multiplied by 1/2. Let's look at my setup here. The result of this will be the original x and y that will feed into the second stage of the transformations. So from the x-axis, from the y-axis, these are the matrices that we could be considering, or the matrix setups that we could be considering. And you can see that what we need to do is take the original x and y and pre-multiply it by that matrix here. So you can see dilation factor of m from the y-axis, that is parallel with the x-axis, is that the new x and y will be equal to the original x and y pre-multiplied by this matrix, where m represents the dilation factor that is from the y-axis, i.e. parallel with the x-axis. So the result of this will give me the original x and y. We pre-multiply by that. It'll give me my new x and y. If we perform that calculation either by hand or on our CAS, we'll end up with this. Going further, we equate, so the new x prime, is equal to a half multiplied by, in brackets, x plus 2. And we want to work out what the original x was. So we multiply both sides by 2. Then we subtract 2. So the original x is equal to 2 times the new x minus 2. We equate y prime with y minus 2. So the new y value will be equal to the original y value minus 2. So if we add 2 to both sides, we get the original y value is equal to the new y value plus 2. Now to begin with, the original equation was this, but we don't want to write it in terms of the original y's and x's. We want to write it after the transformations have taken place. So y is equivalent to y prime plus 2, and x is equal to 2 lots of x prime minus 2. So let's look at the algebra here. At this stage, I should be subtracting 2 from both sides, so this plus 2 there shouldn't be written. So I take 2 from both sides. Now you can see I've got 4 minus all of this here squared. So how is it that we get to this stage? It's very interesting, isn't it? Cut it in there and start reworking this part here. Here we have the original function, y equals, in brackets, 4 minus x squared plus 2. We don't want to write this in terms of the original xy's. We want to write it in terms of the new xy's, which we refer to as being x prime, y prime. So instead of writing y, I write what y is equal to, which is y prime plus 2. Instead of writing x, I write what x is equal to, which is 2x prime minus 2. In my next move, what I need to do here is simply work what's going on here. So 4 take away negative 2 becomes 4 plus 2, which is 6. And I've got minus 2x prime, so I have minus 2x prime in here, all raised to the power of 2, and I've got a plus 2 still. In my next move here, in my next line, I take 2 from both sides, so I just end up with that there. I recognise that within this bracket, that 2 is a common factor. So let's take out 2 as a common factor. So that leaves us with brackets open, 2 multiplied by the bracket 3 minus x prime, close bracket to the power of 2. Now everything inside the brackets is squared, so the 2 is squared, and so too is the 3 minus x prime. So that leaves me with y prime equals 4 multiplied by 3 minus x prime squared. So in other words, the h function, h of x, is equal to 4 minus 3 minus x all squared. Alrighty, so we've got this new function h. Finally, what we have to do is work out the domain and range for this new function h. There's our h function. Now, we're going to begin with the domain of f being negative 3 and 2. And remember, it underwent a series of transformations to become a new function h. So we're going to use that knowledge to help us work out the new domain of h. So x in f was negative 3. What's going to become for h? And then we went all the way up to 2. What's the 2 going to become with the h function? So the new x value, which is a part of the h of x function, x prime is equal to a half of the bracket x plus 2, where x is the original value. So what we're going to do is use that knowledge. So we've got a half, negative 3 comes in for x, plus 2, and if we do the calculation on that, it ends up being negative a half. So the new x value is negative a half. Let's look at what happens there with the original 2 that was a part of f of x. Again, what's going to happen for that point 2, x equaling 2, as far as h of x is concerned? We sub in 2 for x, and we get a result of 2. So that 2 ends up just being a 2. So what we can see here, guys, is that with the original domain for f of x being between negative 3 and 2 including, then the negative 3, because of the transformations, is going to be moved to negative a half, and the positive 2, because of the transformations, is still going to be a 2. So our domain for h is going to be from negative a half to 2, including those both endpoints. The range is the same story. Our range for our original function f of x is between 6 and 51. There's a series of transformations that have taken place to produce a new function h of x, but under those transformations, what does the 6 become and what does the 51 become? Well, we know that the new y value will equal y minus 2. So the original y value was 6, so 6 take away 2 is 4. So the 6 has been moved to a 4. 51. Y prime is equal to y minus 2, so 51 take away 2 is 49, so the 51 has been moved to a 49. So our range for our h of x function is from 4 to 49, including the 4 and including the 49. Now, to produce the range, we could have used a different technique. All right, what we could have done is taken the domain that we found out for h of x and then sub that into the new rule. So remember, the found domain was here. X is between negative a half and 2. The rule that we found out for h of x is 4 lots of 3 minus x squared. So what we should be able to do is substitute x equaling negative a half and then produce the corresponding y value, which we do, and you can see it's 49. Then substitute x equaling 2 into the new h of x to produce 4. And what we can conclude here is that the y values for h of x go between 4 and 49, including the 49 and including the 4. This is in line with what we found out with the other method above here.